I want that to go away. Go away. Okay. This time we are talking about friction. Yay. So far we have just treated friction as FF, and that is absolutely correct. So the main thing that students mess up when I start talking about friction is that they get confused, because I'm about to give you a new equation for friction, and they're like, oh, okay, this is the only way I can solve for friction. Well, no, we've been solving for friction no problem with other examples. A super fast example, if pushing with 30 newtons of force causes a 2 meters per second squared acceleration on a 2 kilogram box, what is the force of friction? So we would draw a free body diagram. Hopefully we're getting pretty good at these at this point. FG, FN, I'm pushing, and I have friction. So my F net and the X direction would be push minus friction. And I'm accelerating, so I'd set that equal to MA. I was given force of push. I was given acceleration. And I was given mass. And now I'm looking for FF. So I would plug in 2 times 2 equals 30 minus FF. So 4 equals 30 minus FF. So FF equals 26 newtons. That is still a way to find friction. You do not need the additional information that I'm about to give you. Now, what I'm going to tell you is that this particular one was an example of kinetic friction because the object was moving. Kinetic means moving. It's the whole point of this word. So this is an example of kinetic friction where the object was moving. Let's do another example. You push on a box with 30 newtons, but it doesn't move. What is the force of friction? So I'm again going to draw a free body diagram. It's the same as the one before. FG, FN, force of push, and force of friction. So my F net equation in the X direction is still force of push minus force of friction. But now it doesn't move. So the net force is 0. I know that the force of push was 30. So 0 equals the force of push minus FF. So FF must be equal to 30. This is an example of something called static friction. Static means not moving. Pretty simple there. Oh, sorry. So notice for both types of friction that I'm about to go over, we can solve it with no more information than what we had last class. I have not taught you anything new. I've told you that there are 2 types of friction, moving and not moving, but that's it. So as a reminder, you can still solve for friction this way. A lot of students, once I show them the next equation, are like, I'm going to throw all of that knowledge out the window. I can only use this equation to find friction. Why don't I have what I need? Bad. So let's talk about it. It turns out that the magnitude of the friction force is dependent on two things. The first is the normal force. That's the connection to the surface, right? The normal force is the surface pushing up on my object. So the amount of that force that the object is being pushed up on by the surface is going to help determine how much friction they have. The more normal force, the more friction. The second thing is what we're going to call mu, which is the coefficient of friction. And it's a measure of the roughness of a surface. The coefficient of friction is typically somewhere between like 0 for ice, no friction, and probably 1.5 for really rough things. It could go up to 3 plus, but those, I mean, you're really going to have a hard time moving at that point. Really, things that are going to be in motion are going to have something that's less than 1.5. It does have no units on the coefficient of friction. So what that looks like is this. The force of friction is equal to the coefficient of friction times the normal force. So that is the force of friction is equal to the coefficient of friction times the normal force. And this is the equation I can use to find the friction force. For example, if I was told a box weighing 8 newtons is moving along a surface with a coefficient of, in this case, it would be it's moving, so what kind of friction would it be? Kinetic friction. We put a little subscript down there to determine whether it's the coefficient of kinetic or static friction. One of them is larger than the other. I'll tell you in a second, but see if you can guess. The coefficient of kinetic friction of 1.2. What is the friction force? So I'm going to still do all of the same steps. I'm going to write out the the free body diagram, FG, FN. I don't know why it's moving. I don't know if it's speeding up or slowing down. The only thing I know is I have the force of friction. So in the F net X direction, I don't know what's happening. I don't know if this box is being pushed. I don't know if it's slowing down. I don't know if some other force is acting on it. All I know is it's moving. It might be being pushed. It might not. I have no idea, nor do I care, because I have a new equation I can use to solve it. One thing I'm always going to have to do, though, to use that is write out the F net Y equation. So in this case, it'd be Fn minus Fg. This box is on a surface, so it is not falling or flying, so its F net is equal to 0. So Fn is equal to Fg. This right here is true a lot, but not always. So double check. Be careful. Don't just make the assumption normal force is always equal to Fg. It's a lot of the time equal to Fg, but write out the F net equation, prove it, then you can use it. So now I know Fn is equal to Fg, which is 8 newtons, because they gave me a weight. I know UK is equal to 1.2, and I'm looking for the force of friction. So FF is equal to UKFN. So FF is equal to 1.2 times 8, which is 9.6. There you go. So I can use this equation to find friction. It's an equation for friction I'm allowed to use. Maybe I use my F-net equations like we did up above to find the force of friction. And then I use the normal force to go back and find the coefficient of kinetic friction. That's possible. But both of these equations can help me find friction. I can do it the old-fashioned way or using this new equation. But let's talk about something because it's important. We have kinetic friction and we have static friction. First off, the coefficient of kinetic friction is UK. The coefficient of static friction is US. UK will always be greater than US. It's not as hard to keep something moving as it is to get something moving. On an atomic level, static friction is larger because those molecules have just had a lot more time to hang out together. The grooves on the tiny, tiny surfaces have gotten more interlocked as they've sat there and pressed on each other. And so it's just a little bit harder to get things to move. So UK is always greater than US. As a reminder, kinetic friction is what we use when something is moving. Static friction is what we use when something is not moving. But here's the most important thing. I'm going to put it in green. The force of friction, kinetic, is always equal to this. Always, always, always. This is the kinetic friction every single time. For static friction, that's not true. The force of friction could be less than or equal to US Fn. It could be up to US Fn, but it's not guaranteed to be US Fn. There's a reason for that. The static friction is a response. So if you push on a stool weighing 8 newtons that has a 1.4 coefficient of static friction, I'll say this, US, save myself some words. US is 1.4 with the floor. If you push with 30 newtons of force, what is the static friction? I might actually need to change my numbers to make sure this works. I do. Sorry about that. I only push with 3 newtons. I'm not pushing very hard, but 3 newtons of force. So you could say, oh, this is no problem. I have an equation for this. FF equals mu S Fn. I'm going to draw my free body diagram to check Fn. So this would be Fg, Fn, F push, and friction. My F net in the y direction would just be Fn minus Fg. This object, this stool, is not flying or falling, so F net y is 0. So Fn is in fact equal to Fg. So you might say, well, I know Fn is equal to 8 newtons, the weight of the stool. I know US is equal to 1.4, so I'm done. the force of friction is equal to 1.4 times 8, which is 11.2. But how would that work? Okay, so then my F net X equation is equal to F push minus FF. So F net X is equal to 3 minus 11.2. So F net X is now equal to negative 8.2. So that means what should this stool be doing? If it has a net force, that means it has to be accelerating in that direction. So this object would have to be accelerating that way. That doesn't make any sense. It's not moving. So the static friction force can't be 11.2 newtons. That is the max static friction force. It is not the actual one, because help me correct this situation down here. This is true, but what does the F net X have to be? It's not moving, so it has to be 0. So actually, the F push must be equal to the force of friction. So 3 is the force of friction, 3 newtons. So this goes back up to what I said about static friction. It could be up to USFN. USFN is actually the maximum static friction force. I have to push with that force to get the object to move. So on this stool, I would have to push with 11.2 newtons of force to get it to move. That's what I have to do. Otherwise, it's not going to move. The instant I apply max static friction and get the object to move, the force of friction becomes this. Now I have kinetic friction. The instant I apply that maximum static friction force and get the object to move, now we're moving. Now the force of friction is less because UK is less. The force of friction is now UKFN. This happens the instant I get up to that max static friction force. As soon as I get it to move, my friction force lowers. So I can push from 0 to 11.2 newtons. From 0 all the way up to 11.19, the force of my push is going to equal the force of static friction. When I apply that maximum static friction of 11.2 as my pushing force, instantaneously I'm going to be pushing that object, and now the force of friction I am pushing against is UKFN. All right? We'll talk more about friction in class.